So AlexNet, the architecture, was very, very close in style to LaNet. So we saw the original LaNet architecture, and it follows a very similar design pattern. So again, when I was talking about those building blocks, we kind of see these building blocks here again. So we have 5 convolutional layers, and each of them followed by a nonlinear activation ReLU function. They're not all followed by max pooling. So for example, here you see we have 3 times a convolutional layer. And at the end of our network, similar to LaNet, we have these fully connected layers that are followed by a softmax layer to give us our probability distribution. So if we look at the architecture, we see that they first start with 11 by 11 convolution. So again, the size of our kernel square was an 11 by 11, and they use a depth of 96 and a stride of 4. And here they use a max pooling of 3 by 3. So again, you can go read the original paper for their implementation. And what's really interesting is also the scale of the number of parameters. So if you recall for LaNet, we were dealing with images that were grayscale. So 28 by 28, 784 pixels. Now we're dealing with these RGB images. Recall that ImageNet had images of 256 by 256. And for practical reasons, they decided to crop these images to 224 by 224, but with RGB channels. So a lot more information coming into our network and a lot more parameters. And in fact, if you compute the number of parameters used between LaNet and AlexNet, you see that there's almost 1,000-fold magnitude difference in the number of parameters that were used. Another interesting thing is that AlexNet used dropout in the fully connected layers. So what is dropout? This was a technique that was relatively new. So dropout is really interesting in that what we do in the fully connected layers is every time during training, at random, we turn off some connections with a probability of 0.5. So if these are our fully connected layers, every time we're going to pass through our network, we're going to, at random, again, we just flip a coin, and decide that some of these connections are going to be dropped. And this can be thought of as a form of regularization. So it kind of forces our network to not depend too much on all the information that's there. And I really like how they mentioned this in the original paper. They kind of think of it as a way of training many models at the same time. In fact, training the original AlexNet model took a few weeks. So you can imagine that if you wanted to train many, many different models, it would take a very, very long time. And they didn't have that kind of time or resources. So they came out with this dropout technique, and they found that it made their models converge a lot better and reduced the impact of overfitting. AlexNet is, again, a very central piece, a very central model in convolutional neural networks. And you can see just from the citations from Google Scholar, they're cited over 43,000 times. This is a very, very high number for a paper. So again, it's cited in almost every paper that you'll read about convolutional neural networks, and it was really one of the backbones. And people really started paying attention once they saw that convolutional neural networks could actually be made to converge to have better performance than handcrafted features on ImageNet. And I really like also this quote from the paper from Alex Krzyzewski and al., and they say, "All of our experiments suggest that our results can be improved simply by waiting for faster GPUs and bigger data sets to become available." So they already had this insight that already, the GPUs that they were training on were simply too slow. In fact, they had to do all sorts of tricks to get their models to converge. They were one of the first to actually put their deep learning models on GPUs, right? They had this intuition that, well, the GPU was really optimized to do matrix calculations, but at the time there wasn't TensorFlow and PyTorch around where you can just say device equals GPU and switch your model over to GPU. They actually implemented all of the GPU operations in CUDA just for this paper, and they released the code with it as well. And there also were some engineering details. So the original AlexNet model didn't even fit on a single GPU. So they were already figuring out tricks to train their model on 2 separate GPUs simultaneously. And again, all these details in the original paper. And it's very, very impressive work because you can only imagine how much time must have been spent figuring out if they were even doing the right thing without even knowing if this would pay off or not. So we were in 2012. And now people really start paying attention, right? And they say, well, what is this deep learning thing? Why is it working so well? And it was a drastic difference in the performance. So all of a sudden, it becomes almost an arms race to find the best deep learning models. And this was a challenge primarily from an engineering perspective, right? Because you have a limitation in hardware. It takes a very long time to train these models. I think it was the order of a few weeks to train AlexNet. And it was also from an algorithmic perspective. You have all sorts of problems that start arising once you start training your network. So you have problems of overfitting, you have problems of underfitting, you have problems with the fact that you have lots of hyperparameters. So just the structure of your network. All of a sudden, we have this network that works, but nothing can really tell us that this is the best network. There might be many different other networks out there. So this was really, again, like I mentioned, an important turning point for deep learning. And now we're going to look at different models that came afterwards.